and welcome to this third lecture on our course on blockchain and its applications. I am Professor Shamik Shural from the Department of Computer Science and Engineering at IIT Kharagpur. I will start the discussion on some of the basic cryptographic primitives which are required for actual implementation and execution of blockchain operations. So, this particular lecture which is the third lecture in this series, it is titled as Basic Cryptographic Primitives, and this is the first part of it. In this lecture, we will cover some of the cryptographic primitives as already mentioned in the earlier lectures that are useful for blockchain. From the earlier lectures, we have understood that the very basic technology of blockchain is built on top of certain cryptographic primitives. By primitives, we mean that these are some of the fundamental concepts and techniques that are used for implementing blockchain in real world, and we will see that there are several such cryptographic primitives which are of use in blockchain. And in this particular lecture, we will talk about hash functions. Some of the keywords that are important for this lecture are as follows. First of all, we will talk about what are called hash functions. We will understand what is meant by hash function, what are its properties and how they can be used meaningfully. We will also talk about one of the hash functions, namely SHA-256 in detail. We will also see that there are of course, there are different characteristics of hash functions. Among them, we will look into one particular property in detail, which is what is called its puzzle friendliness, and we will see why this property is very important as we try to apply hash functions in the context of blockchains. So, today what we will learn, including this lecture and the next few lectures, actually from lecture starting from lecture 3 and then 4, 5, 6 and 7, we will talk about these basic primitives behind the blockchain technology, and we will talk about cryptographically secure hash functions. Also, we will talk about digital signatures. So, these are two different concepts, although there is some relationship between them, as we will see as we progress. And this first lecture we will talk about hash functions. The hash functions, what are these? What is the importance of these hash functions in the context of blockchain? Why are we studying hash functions? The reason is that these hash functions and their certain ways of constructing different data structures that can be used for connecting the so called blocks in a chain in a very importantly in a tamper proof way, and that is what we will see later essentially defines what a blockchain is. We will also talk about digital signature. By digital signature, what we mean is that just like manual signature, when we sign a particular document, there we ensure that anyone who checks the document later would know that it has really come from me, because the signature will match with my physical signature. Not only that, when we put a put a regular signature on a piece of document, it also guarantees that later on I cannot deny that I had indeed signed the document, because that document due to its signature which belongs to me, which can be verified, it can also prove that it was indeed me who had signed the document, so that there is no possibility of later denial from my side as well. Just like these manual signatures, there is also this concept of digital signatures, so that one can digitally sign the data and later on no one can deny about their own activities, and further others also can check whether it is authentic. So, this is very interesting concept which we will see as an important building block for blockchain technology. So, overall during these 5 lectures, we will cover the concepts of hash functions as well as digital signatures. We will start with our discussion on hash functions. So, what is a hash function, and more specifically we are talking about cryptographic hash functions. Okay. So, these are like functions as we know them, that take some input and then produce some output, and the property that makes such functions really cryptographic hash functions are as follows, that they take any arbitrarily sized string as input. So, the input we denote by the letter M, uppercase M, which represents the message that will be converted into what we call the fixed size output, often also called the message digest. Okay. So, for the function there is an arbitrarily sized string as input, and the size of the output is fixed. That is very important, and we will see why that is really required for such cryptographic hash functions. And there are various types of hash functions, various types of cryptographic hash functions also, and they generate outputs of different sizes. For the kind of applications we have in this domain of blockchain, usually the size of the output of these hash functions we will consider to be of 256 bits in length. Okay. So, the output h of m. So, if I denote the hash function as capital H, then the output h of m is what we call as the message digest. Okay. So, we have the message as input and the message digest as output for the hash functions. What is very important is that such types of functions, taking the input m and generating its digest, it should be very efficiently computable, because it will be used again and again and again while we construct a blockchain. Okay. So, it is very important that the generation of the message digest from the message is very fast, computationally it is efficient. Some of the important properties now that we will study for cryptographic hash functions, these are as follows. First and foremost, they should be deterministic, meaning given a hash function and given a particular message m, it will always generate the same digest h m for the message m. That is important. So, there should not be any randomness in it, because what we want is that we should be in a position to repeat the same application of the hash function on the same message, and we will be able to check that we are always getting the same digest as the output. Second property, which is what is called collision free. So, this is an important property of cryptographic hash functions. What it means is that if there are two messages which are different, then their digests also should be different, meaning that if I have a message m1 and another message m2, then the digest of m1, that is h of m1, should not be the same as the digest of m2, that is h of m2. Third important property is that hiding of the original message information. Now, what does it mean? It means that if I have a message m1 and I apply the cryptographic hash function on m1 to get its digest hm1, and then I have another message m2 for which I get the digest m2 hm2, then by looking at these two digests hm1 and hm2, I should not be able to figure out that this what would be the m2 that would generate that hm2, meaning that even if there are small variations in m1 and m2, the digests, the hm1 and hm2, they should not be similar. Okay. That means that knowing a particular message m1 and its digest hm1, I should not be able to predict that for message m2 what would be the digest hm2. Okay. The fourth important property is what is called puzzle friendliness, meaning that given x and y, that is two strings of which say x is a message and y is output of a hash function. Now, given x and y, we would like to find out a k such that y is the hash of x concatenated with k, meaning that given x, can we determine a k so that the hash of x concatenated with k generates a y, and this y will have certain properties that need to be satisfied. Okay. So, this is what is called puzzle friendliness, and it is very commonly used for solving what we call as the mining puzzle in one of the blockchains like Bitcoin, and it is one important pillar of construction which is called the proof of work. Of course, in other blockchains also similar concepts can be used, but we will discuss this concept of proof of work in more detail in the context of Bitcoin blockchain. Now, we mentioned about the collision free property. Okay. So, these hash functions are one way functions, meaning that given x, it is very easy to find h x, as we said that it should be efficiently computable. So, h x can be obtained very efficiently from x. However, given any h x and not knowing x, we cannot determine x. So, this is a very important property that this cannot be an important property that we cannot determine x from h x. This is one of the reasons why these are called cryptographic hash functions, and very important that we have this property always satisfied when we are using it in the context of blockchain. Now, giving a simple analogy, though it does not really guarantee all the properties of cryptographic hash functions, it is for ease of understanding what we mean by these one way functions. A very simple example could be that given any number and we are told to find what is its cube, we can very easily do that. Suppose we are given 3 and we know that the cube will be 27. Now, getting back the cube root may not be that easy. Okay. Of course, for 27 we know that the cube root is 3, but given any other number for which we do not know what the cube root is, then the complexity of finding cube root is more than the complexity of finding the cube. Of course, we can always get back the cube root. So, it is not really a one way function, but hash functions are such that you cannot really get back to x given a value of h x. Okay. Also, it is difficult to find two messages x and y where x is not equal to y, but their hashes are the same. So, this is also an important property which tells us that there cannot be collisions, that for two different x and y the hashes are different. Okay. Then of course, the phrase difficult to find means that there could be certain collisions. So, it is not really impossible, but it is going to happen very, very rarely. If we want to randomly choose inputs to find out a collision, we can try that out a very large number of times, but it will take too long to actually get back two digests which are the same for two different messages. So, how do we guarantee this property of collision freeness? So, for some hash functions it might be pretty easy to find collisions. For example, we know about this concept of birthday paradox, which says that what is the probability that in a set of n randomly chosen persons, suppose in a room there are n persons, and what is the probability that some of them will have the same birthday. Now, if we see that by applying the simple concept of pigeonhole principle, the probability reaches 1 when the number of people reaches 366 if it is not a leap year, or 367 if it is a leap year, because at least two of them now will have the same birthday. Of course, that is quite obvious, but it can be shown that even with only 70 people, the probability of two persons having the same birthday reaches a probability of 0.999, and even with only 23 people, it reaches a probability of 0.5. That means, although it might appear that the number of persons you would need to reach that probability of two persons having the same birthday very high, value, it is not actually so. Even for a smaller number of people, you could reach that probability very quickly. Of course, the birthday paradox places an upper bound on collision resistance, okay? And it is also important that we are not talking about birthday paradox in the sense that there are only 365 or 366 possible values. Rather, we are talking about a very large possible values of the message digests, and that is the reason why we generate digests, so that the lengths of these digests are really high, and typical values, as we had mentioned before, are like 256 bits. And for a hash function that produces n bits of output, like say n is 256, and it can be shown that an attacker needs to compute 2 raised to the power n by 2 hash operations on a random input to find two matching outputs with a probability which is greater than 0.98. To put it in proper perspective, for a 256 bit hash function, the one that is used in blockchain, usually the attacker needs to compute 2 raised to the power 128 hash operations, which is really time consuming. Even if each hash can be computed in 1 microsecond, it will take close to 10 raised to the power 25 years to find out two such messages which have the same hash value. So, we can conclude from this that if we have sufficiently large lengths of the message digests, that is, if we choose a hash function so that the digests are of length say 256 bits, then it is practically impossible to come up with two different messages that will result in the same value for the digest. Now, another important use of hashes is that it can be used as a message digest. Meaning what? It means that since h x is equal to h y, it is safe to assume x is equal to y, meaning that if we see there are two digests which are same, then we can safely assume that the original messages are also same. That means the digests effectively are unique representations of the original messages. So, we can simply remember just the hash value rather than the entire message, and this is what is called the message digest. So, effectively it means that say there is a very long document D1. Now, in order to later on use this document with its certain unique properties, we do not need to keep remembering this whole document D1, rather we could generate its digest, say h of D1 equal to M1, that can be used for remembering this particular message. And if we want to check if two messages x and y are the same, that is whether x is equal to y, it is simple that we say, just check if h x is equal to h y. And this is efficient because the original documents could have been really long, but as we mentioned that the property of hash function is such that the output is of a fixed length. Hence, it is very efficient that we simply compare the digests to check whether the original messages are same or not. Having said that, let us take an example where we can actually generate hash functions for certain types of messages. And we can go to this particular site, and there are many such sites which are available online, and this particular site basically is the supplementary information and such data that is available with respect to the book called Blockchain Basics, a non-technical introduction in 25 steps by Daniel Drescher. So, we will see this illustration here where we will give certain messages as input and we will see what their hashes look like. So, let us go to this site as was mentioned and let us type say hello world, okay, and there we then say that okay, we want to calculate the hash value. So, we click on calculate hash value and we see in the output the hashes for various types of hash functions. So, this MD5, SHA-1, SHA-256, SHA-5112, these are all examples of hash functions, and we notice that the sizes of the hashes that we get, these are of different lengths. And specifically, if we look at SHA-256, we see that it is shown using 64 such hexadecimal digits. As we can see that each of these are like A, 5, 9, 1 and so on. So, each of these is a hexadecimal digit and there are 64 such. So, overall the length in bits is 256. If you give another such message as input, say I just write hello world and 1 and then we calculate the hash value. So, I click on calculate hash value once again and we get once again the hashes, and if you notice here there are 2 points which are important. First of all, you can see that it is very easily computable. Just as I click on the button calculate hash value, immediately we see that the hashes are displayed. So, that means that it is efficiently computable. Second point to note is that the hashes could be of various lengths depending on the type of hash function that we are using. And third point, which is very important, is what we mentioned as the avalanche effect, is that just because I changed this input text by only a small value, like I put a space and then 1, immediately we see that the output hash is completely different. So, if you had noticed that the hash for hello world and the hash for hello world space 1, these are completely different. That means, just by looking at the hash and knowing that what is the hash for a given input, you cannot figure out what is the hash for the one for which you do not know. For the, if you know the hash, then from there getting back to the original message becomes very, very difficult. So, just because I know what is the hash for hello world, then looking at the hash for the second one, I cannot figure out that the original message for this was hello world 1. So, that is an important property of the hash functions, and that is what we have already explained, and this particular illustration also demonstrates that. So, you can try it yourself by going to this particular site or going to other sites where you can give any input and then you can generate the outputs. Next, we talk about information hiding through hashing. So, given an hx, it is computationally difficult to find x, as we said, and the difficulty depends on the size of the message digests. We have seen that. So, now hiding helps to commit a value and then check it later, meaning that suppose there is a particular value initially, say x, and then we create its hash and then we store it, okay. And later on we want to see what was stored. So, if we later on claim that we had stored say y, then running hash on y, whatever we get as the digest, that should match with the original digest that was saved, okay. So, it can be confirmed that the message that was originally committed, that can be shown to be the same as the one that now one is claiming to be the original message by comparing their hashes. So, instead of first of all comparing the original messages, we can compare them efficiently, and more importantly that if the hash was generated and stored somewhere and not tampered with, then later on if somebody claims that, oh, what was stored originally, let us check, and then if it is claimed that y was stored instead of x, it can be easily verified that the hash of y is not going to match with the hash of x that was originally saved. So, only when the hash of y matches with the hash of x that was originally saved, one can confirm that y indeed was the message that was originally saved or was stored in the digest store. So, this is one of the important uses of hashing, and again this property will be used in the context of blockchains. Now, we show here through a simple picture that say Alice has committed the hash and she has saved the hash of a message m along with that of what we call her public key. We will talk about this public key concept a little later in one of the lectures. So, what is done is that the message m and the public key of Alice, that is k a, along with the hash of the message M and public key of Alice K A, these are all passed on to Bob, and Bob can easily verify whether this was indeed the message that was stored. So, in this case what we see is that the hash which was stored can be now checked by running the same hash function on M and K and checking whether that is matching with the original hash. And same verification can again be repeated by Jane, who also can run the same steps to check whether indeed that M was the message that was stored by Alice. And later on we will see that how Alice also cannot deny that it was indeed a message that was stored by her. Now, the property of puzzle friendliness. So, if M is chosen from a widely spread distribution, now it is computationally difficult to find a K such that Z is equal to H of M concatenated with K, where M and Z are known a priori. So, that means that we are saying that your message is say M, now determine K, that is the solution to the puzzle, so that the hash of M concatenated with K will generate Z. Now, of course, this Z is not always something that is given, rather that certain properties of Z are mentioned, so that this hash of M concatenated with K should satisfy those particular properties. So, effectively we can say that Z is acting like a set of possible values instead of one particular value. So, this puzzle friendly property implies that random searching is the best strategy to solve the above puzzle, and we will see that actually in the process of what we call mining in different blockchains like Bitcoin, solving the puzzle is a key concept that is used there, and while hash functions are puzzle friendly, solving them is not really always that simple. So, to conclude this lecture, what we have seen so far is that we have discussed what is meant by a cryptographic hash function, what is definition. We have also seen certain properties of hash functions that need to be satisfied, so that they are of use, and also we have seen that how hash functions can be used, for example, for storing some message in the form of the digests, comparing two messages by their digests. So, these are some of the useful uses of hash functions, and also what we will do is that we will later on see that these types of uses we have seen in general context, how they can be actually used in constructing blockchains in any known blockchains like say Bitcoin or Ethereum or other types of blockchain. So, these are the important points that were discussed in this lecture, and these are the references, some of the references. One is the blockchain basics, the book that we have mentioned, which has this supplementary material on the web which you can make use of. Also, you can get more details about these hash functions from the book called Cryptography and Network Security Principles and Practice by William Stallings. And there are of course a lot of other books on cryptography and network security there that also talk about different types of hash functions, their properties. So, with that we conclude this lecture, and we will talk about more details of uses of hash functions and how they can be used in the context of blockchain in the subsequent lectures. Thank you.